Hello everyone, welcome to Chem 1050. This is Professor Walrath and this is chapter 1. As we get into chemistry, we might ask yourself, what is chemistry? Well, it's all around us, whether it's the pressure cookers that we use in our kitchen, the salt that we put on the roads to keep them from being a sheet of ice, or the barbecue that you have in your backyard. So a good definition of chemistry is it's a field of study concerned with the characteristics, composition, and transformation of matter. So as we get into chemistry, there'll be some terminology that you need to memorize and understand, and one of those being matter. Matter is anything that has mass and takes up space. It includes naturally occurring things, both living and non-living, things that we can see, like cell phones and computers, plants, rocks, and soils, as well as non-living things, such as the air and the bacteria that are constantly present. And then there's another term, mass, which is the amount of material that we can pack into a substance. As I mentioned on the previous slide, matter does include anything that could be non-living or living. Examples are plants, soil, air, bacteria. Things that are excluded from things being considered matter would be forms of energy such as heat, light, and electricity. Matter can be naturally occurring as well as synthetic, can be produced in a laboratory setting. And the universe is made up of these two different things, matter as well as energy. So here we have a little quiz. We're trying to classify each of the following as either matter or energy. And chances are, if you can write a symbol from it off our periodic table, then it's going to be matter. And Ag happens to be our symbol for silver. That is definitely matter. Can't write a symbol for cake, but there's lots of sugars and other ingredients in there. That is definitely matter as well. Heat, however, we cannot make a formula for, and it comes in various forms. That is definitely a type of energy. And water, hopefully you know this chemical symbol for that. That would be an example of matter as well. For our class, matter is going to come in 3 different phases or states. There's solids, liquids, and gases, which I'm pretty sure you're all familiar with, but we need to be able to define them a little bit better than that. So we're going to say that a solid has definite shape and a definite volume, and you can measure both of those. If you were to take an example of a rock or a coin, you can definitely try to figure out what the shape is and what the volume is. The next one is a liquid, where it has an indefinite shape, but it has a definite volume. We could measure it in the lab with a graduated cylinder or a beaker. It is, however, going to take the shape of its container. And the final state of matter is gas, and that doesn't have a definite shape or a definite volume. That gas is going to fill its container completely, and it's going to take the shape of that container. Depending on the substance, that substance can exist in different states depending on the temperature, the pressure, and the strength of the forces holding those molecules together. And hopefully you know that solids, the molecules or the particles would be held together with a great force. There's not a lot of movement in those particles, maybe a little bit of vibrations. Liquids, they're much more fluid. There's still attractive forces there, but they're able to slide past one another as far as the molecules go. And with the gas, there's no attractive forces. They want to be far away from each other as possible. On these questions, I always encourage you to pause the video, read the questions, try to answer them for yourselves, and then come back and see if you are correct. So this is, and all these questions come out of the back of your book. It goes along with the chapter number and the question for that particular chapter. What physical characteristic distinguishes a liquid from a solid? And hopefully you would go back and review those if you weren't sure, but liquids have an indefinite shape, while solids have a definite shape. Similar questions between gases and liquids, and after going back and reviewing their characteristics, gases have an indefinite volume while liquids have a definite volume. And there are your answers. Hopefully you were correct. Questions. Here are some questions that help you use the knowledge that we just talked about. So, excuse me again, these are questions that you should pause the video, try to answer for yourselves, and then come back and see if you can figure that you got them right or that you need a little bit of time to review that material. So what physical characteristics is the same for liquids and solids? And hopefully you would say that is a definite volume. Similar question between gases and liquids, and hopefully you would say that's an indefinite shape. And here are your answers. Hopefully you were correct. Here are some pictures of solids, liquids, and gases. Hopefully you know that A is a solid, B is a liquid, and C is a gas. But if we were to, again, describe the characteristics of A, it's a solid, it has a definite shape and a definite volume. Where B, the liquid, has an indefinite shape. It takes the shape of the cylinder that it's in, but it does have a definite volume. We could measure that, and it looks like it's a little bit under 40 from the picture. And C is a gas. Notice we have some film on top of there that's trapping the gas. It is taking the shape of the container and it's filling it completely because it doesn't have a definite volume or a definite shape. Here is another picture just showing you that water can be found on all three states of matter on the earth, and hopefully you can see out in Yellowstone National Park we have some steam, we have some frozen snow, and we have some liquid water in the stream. Section 1.3 is dealing with properties of matter. And a property is just a distinguishing characteristic that helps to be used to identify and describe that particular substance. So here's a couple examples. Water has many properties, but one of them is that it's a colorless liquid. It freezes at 0 degrees Celsius and boils at 100 degrees Celsius at 1 atmosphere of pressure. Another example of matter would be petroleum, and this can be burnt to produce energy. And the differences here are going to help us distinguish between two different types of properties, whether they are physical or chemical types of properties. And that's what we're going to explore in the next few slides. To elaborate a little bit more on those two different properties that we mentioned in the last slide, physical properties are characteristics that can be observed without changing the basic identity of that substance. Some examples would be color, odor, texture, taste, physical state, whether it's solid, liquid, or gas, melting points, boiling points, and the hardness of that substance. While a chemical property, on the other hand, these are characteristics of a substance that can be described in a way that it undergoes or resists changes to form new substances. So here's an exercise that we'll use to try to classify the changes that are taking place, or the type of property that is undergoing here. So we're going to try to classify each of the following as a physical or chemical property. When you're out in a campfire and you're roasting marshmallows, when it turns black, that is a chemical reaction. You cannot get your marshmallow back. The fact that zinc is solid at a room temperature, that is a physical property. And when rubbing alcohol is rubbed on your skin and evaporates, that is a physical property as well. Here's another learning check. I always encourage you again to pause the video, see if you can answer these questions, and then see if you're right. So we're going to classify each of the following properties of the metal magnesium as a physical property or a chemical property. Part A, solid at room temperature. Hopefully you would guess that that is a physical property. Ignites upon heating. That is a chemical property. We're going to get a fire, probably it burns very bright. You don't want to look at it. We will do this in the lab and you'll see that. And if you were to look at it, you should look through it through special glasses. Part C, hydrogen gas is produced when it's dissolved in acid. We're getting something new here. That would be an example of a chemical property. And magnesium has a density of 1.738 grams per centimeter cubed at 20 degrees Celsius. That is an example of a physical property. Hopefully you got all those right. For the next section, we're going to look at changes in matter. And the first change in matter that we'll look at is a physical change. This is a process in which a substance changes its physical appearance, but its chemical composition is not changed at all. No new substances are formed as a result of a physical change. Maybe you change the shape. Some examples would be boiling, freezing water, cutting, bending, splitting, breaking, all examples of physical changes. You still have the same substance after you've boiled it or froze it or cut it, bend it, split it, break it, whatever have you. So just to reiterate from our previous slide, physical change is a process in which the substance changes its physical appearance but not its chemical composition. The other type of change that we'll discuss is a chemical change, and this is where the substance undergoes a change in composition and a new substance can be formed. A lot of times we look for certain characteristics or certain conditions, a change in temperature, a change in color, production of a gas, or the formation of a precipitate would all be examples of chemical changes. Here's a nice picture showing you the term chemical, and usually the term conveys the idea that the composition of a substance does change. Some examples might be the flammability, or the fact that it's decomposing at a certain temperature. Here's another learning check for you. And I always encourage you again to pause the video, see if you can answer the question, maybe even go a step further and classify each of the following as a physical or chemical change. So in this question, which of the following are examples of a chemical change? Pulverizing or crushing rock salt. You still have rock salt or salt when you're done. Burning wood, you cannot get your wood back. You have ash, you have smoke. That's a definite chemical change taking place. Dissolving sugar in water might be challenging, but if you were to evaporate the water, you would get your sugar back. Same thing is true with melting a popsicle. If you could collect that popsicle and put it back in the freezer, you could get your popsicle back. Another learning check for you. Again, I know I repeat this often, but pause the video, see if you can answer these questions, and come back and see if you got them right. So we're going to indicate whether the following statements describes a physical or chemical property. For A, silver salt discolors the skin by reacting with skin proteins, and the key word here is reacting. So in this case, we would have a chemical property. Hemoglobin molecules have a red color, and that would be a physical. We're just talking about the red color. Letter C, beryllium metal vapor is extremely toxic to humans. That would be chemical. The toxicity of beryllium indicates that it produces a change in substances in the human body that can be potentially lethal. And the last one, D, Aspirin tablets can be pulverized with a hammer. That's another example of a physical property. We're just changing its shape. Here's another learning check for you. We're going to classify the following as changes as physical or chemical. So a newspaper is shredded. That is physical. Mechanical changes are physical changes. Okay. Molten candle wax solidifies in a mold. That's another example of a physical change. It's a change in state from a liquid to a solid in this case. That's always a physical change. Container of refrigerated milk sours. You cannot get your milk back. That's a chemical change. And maybe you don't want your milk back. Maybe you want whatever's left afterwards. And fingernails are trimmed. You still have fingernails after you cut them. No new substances was formed. For section 5 of chapter 1, we're going to try to start breaking down matter into whether it's a pure substance or mixtures. Pure substance is a single kind of matter that cannot be separated into its other kinds of matter by ordinary physical means. Here's a couple examples: water, H2O, or carbon dioxide, CO2. The other type is a mixture, and then we'll see that there are two variations of each one of these, but a mixture is a physical blend of two or more substances in which each substance keeps its own unique identity. Here's an example of seawater. Starting to look at mixtures in a little bit more detail. Mixtures do have a variable composition, and really there's two different types. The first type is sometimes known as a solution or a homogeneous mixture. This contains only one distinct phase, which has uniform properties throughout. The other type of mixture is known as a heterogeneous mixture. This contains visibly different phases or parts, and each part has its own unique properties. Here's a chart breaking down matter, and just for a refresher, matter is anything that has mass and occupies space. Pure substances, they should really have another piece coming off here, just like mixture has two different parts, and I'm going to try to draw it on here, where we could have an element, or we could have a compound. Where mixture, it is a physical combination of two or more substances, and again the two different ones are the homogeneous mixture, which only has one phase, and the heterogeneous mixture, which has two or more phases. Here is another learning check for 1-5, and we're trying to figure out which one is a homogeneous mixture. Again, I encourage you to pause the video, take a stab at it, and see if you can get it. Once you come back, hopefully you see that our homogeneous mixture is gasoline. It has octane, it has other types of substances in there, maybe shorter or longer hydrocarbons. Everything else would be heterogeneous, or just a compound or an element. Okay, but the only homogeneous mixture there is the gasoline. Another learning check for us. For 1-25, we're going to assign each of the following descriptions of matter to one of the following categories, either a heterogeneous mixture, homogeneous mixture, or a pure substance. So when you look at A, two substances present, two phases, that's kind of the definition of a heterogeneous mixture. Part B, two substances present, only one phase. That is a mixture, but it's a homogeneous mixture since it's only one phase. Letter C, one substance present, two phases present. For C, we are looking for a pure substance, two phases present to form one substance. For an example, ice and liquid water. And the last one, D, 3 substances present, 3 phases present, that is a heterogeneous mixture. The existence of 3 separate, distinct phases indicates a substance that are not uniformly mixed. 1-6 is talking about elements and compounds, and that's where I kind of broke down matter. An element is a pure substance that cannot be broken down into ordinary, simpler pieces by ordinary chemical reactions, such as using electric current, heating, or a beam of light. We would need something much more sophisticated like a cyclotron center like they have at Michigan State. Here's a couple examples: gold, silver, copper. Compound is a pure substance that can be broken down into simpler substances, and they're going to have completely different properties than the original substance has. So if we were to take a beaker of water and submerge a 9-volt battery in there, you would notice bubbles coming off each of the terminal. Hydrogen and oxygen would be produced, and hydrogen and oxygen have completely different properties than the water that they came from. You would, for instance, use water to put out a fire, where if you were to try to use hydrogen or oxygen to put out a fire, you'd be in for a big mess. Those are both extremely flammable gases. So here's some other examples of compounds. Here's a good review to distinguish between compounds and mixtures. Compounds have properties distinctly different than those of the substances that are combined to form that particular compound. The components of a mixture retain their properties. You can taste the salt in the water even though you've mixed them together. Compounds have a definite composition. You could write a formula for it, while mixtures have a variable composition. The lemonade that you drink at your house might be different than what I have at my house. The mixtures, again, we can have different likes for the amount of sugar that we put in there. And physical methods are sufficient to separate the components of a mixture. Components of compounds cannot be separated by physical means. Chemical methods are required. Section 7 of chapter 1 is looking at the discovery and abundance of elements. There are 117 known elements. 88 of them are naturally occurring, and 29 of them have been made in the laboratory. These can be found on our periodic table of elements in your textbook. Studies of radiations emitted by stars enable scientists to estimate the elemental composition of the universe. As a result, in this pie graph, you can see 91% is hydrogen, 9% helium, less than 1% is all other elements. So that tells us that our universe is relatively young and we have a long way to go before it dies out. All the other ones are mere impurities compared to the others that are dominant there. Here's another learning check. Again, I encourage you to pause the video, try the questions for yourself, and come back and see if you got them right. 1-29 states, from the given information, classify each of the following pure substances A through D as elements or compounds, or indicate that no such classification is possible because of insufficient information. So on part A, analyst with elaborate instrumentation indicates that substance A contains 2 elements, and that would be a compound. A single substance A is made up of 2 elements as a compound. For B, substance B decomposes upon heating. That is a compound again. B must contain more than 1 element to decompose chemically, so it has to be a compound. C. Heating substance C to 100 degrees causes no change in it. Classification here is not possible. There's just not enough information that's available. And D. Heating substance D to 500 degrees causes it to change from a solid to a liquid. And again, not enough information is really possible to make any type of distinguish between any of those substances. We are nearing the end of chapter 1. This is section 8, dealing with chemical symbols. And when we look at the periodic table, we have 1 to 2 letter designations for all elements that are on there. First one is capitalized. Second one, if present, is always lowercase. Chemical symbols, again, first one is capitalized. If there is a second one, it's not capitalized. Here's a few examples. Capital H is hydrogen. Notice the second one and everyone after, there are 2 letters. First letter is capitalized, second one is always lowercase. Sometimes they make sense, sometimes they don't. Like Ba, you might know is barium. Co, notice it's the capital C and a little o, that's cobalt. And where if we were to write all capital letters, that would be carbon monoxide for capital C, capital O. Something like this. Pb comes from a Latin name, that's plumbum, but it's lead in our language. And Ag, again, a name from a Latin, that is silver. This slide is just saying that some elements come from Latin names, some are named after scientists, some are named after colors. We get names from all over the place. So here are a few that had come from Latin origins. And on page 16 in your text, there happens to be a list of elements and what their names are. You'll never have to memorize them. Hopefully you'll always have access to a periodic table that you can use. At least when you're in person, you are. Here's another learning check for us. We're going to give the name of the element denoted by each of the following chemical symbols. So Li stands for lithium, He stands for helium, F stands for fluorine, and Zn stands for zinc. Another learning check just to see if we're getting familiar with our periodic tables. We're going to write the chemical symbol for each member of the pairs of elements. So copper is Cu. Let me try that again. Cu, and cobalt is Co. Potassium is K, where phosphorus is capital P. Iron is Fe, while iodine is I. Silicon is Si, and silver is Ag. On to our last section of chapter 1. Thanks for bearing with me. To define an atom, this is the smallest particle of an element that can exist and still have the properties of that element. They're extremely small, nothing that we can even visualize. In fact, if we were to look at 1 inch, it would be 254 million atoms that could line up next to each other. And sometimes books might put this in scientific notation, so it would be 2.54 times 10 to the, in this case, 8th atoms across that particular inch. So this will be something that we look at in chapter 2, where we write a number between 1 and 9.9 raised to a power of 10. That's scientific notation. Molecules are groups of 2 or more atoms that function as a unit because the atoms are tightly bound to each other. Behaves in many ways as a single distinct unit. They can be diatomic, they can be triatomic, or they could be tetra, penta, so on and so forth. So you're going to have to memorize just a few prefixes here, and hopefully those ones make sense to you. Some more terms that the book throws around would be homoatomic molecules, which are made up of just one type of element. So here's a few examples: hydrogen, oxygen, nitrogen, chlorine, phosphorus. They don't always just have to be diatomic, but they can be like this as well. Some of the diatomic ones that we should recognize would be brother Hoff-nickel. Your brother will always be there to try to help you out. If you see one of these elements by themselves, just like hydrogen or oxygen or nitrogen or chlorine, they're always going to be diatomic. So remember, your brother Hoff-nickel is always there to try to help you out. The other term that your book uses for atoms and molecules are heteroatomic molecules, where the molecule is made up of two or more kinds of atoms. So you must have two or more substances like water, carbon dioxide, dinitrogen tetraoxide, or in this case a disaccharide for the last one there. Here's some pictures showing some heteroatomic atoms. Notice there's an A and a B in each one of those, also denoted by the different sizes and different. A couple of learning checks for us. We're going to look at this particular compound, xenon tetrafluoride, and try to figure out, is it diatomic, triatomic? Well, it's actually 5 of them in there, so if we count up all the atoms, 4 fluorines, 1 xenon, that would be pentatomic. Is it homo or heteroatomic? Well, it's made up of different substances, so it'd be hetero. And is it an element or a compound? Well, it's a compound because it's composed of 2 different types of atoms. For this learning check, we're going to try to classify as an element, as a compound, or it could be an element and a compound. So molecules are triatomic. It could be an element or a compound. Molecules contain only one type of atom. That would be a great example of an element. Molecules are heteroatomic. That must be a compound. And our last one, molecules are both homoatomic and diatomic. That's an example of an element. Here's another learning check for us. We're going to look at the pictures and we're going to try to answer the questions A through D based on those pictures. And for A, which diagram or diagrams represent a compound whose molecules are triatomic? Molecule is going to be the same throughout, and that is going to be diagram 1. Which diagram represents a mixture of 2 compounds? For B, we're looking for 3. For C, which diagrams represent a mixture that contain 2 different diatomic molecules? And we were looking for diagram 2. And this one. And the last one, which diagrams represent a pure substance? And we were looking for diagrams 1 and 4. Our last section, chemical formulas. This is a notation made up of chemical symbols of elements represented in a compound and contain subscripts located down to the bottom right of each chemical symbol that indicate the number of atoms present in a particular molecule or compound. A couple examples. H2O, notice there's 2 hydrogen per every 1 oxygen. Here's another one that has a polyatomic ion in it. This is calcium phosphate. There are 3 calciums, and then you got to be careful because this 2 gets distributed to everything in here. So there's actually 2 phosphates and 8 oxygens. A couple learning checks for us. We're going to try to figure out how many atoms of each element are present in the following compounds. Sulfuric acids, we would have 2 hydrogens, only 1 sulfur, and 4 oxygens. And don't forget things in parentheses, that 3 outside the parentheses gets distributed. So 2 irons, 3 carbons, and 9 oxygens. Our last learning check. Thanks for bearing with me and making it through this presentation. For 1-75, we're going to indicate whether the following chemical notation is a chemical symbol for an element or a chemical formula for a compound, and also how many atoms are present. So hopefully you could figure out for A, that's definitely a compound, and if we look at the number of atoms present, there's going to be 6. Next one is also a compound, and if we look at the number of atoms and count up everything properly, there will be 5 atoms. This is an element, just one type of element, and there's only 1 atom present, and another compound, and there are 2 atoms present.